Now we have gotten to chapter 7 of the book, which is mostly focused on the theoretical motivations of graph neural networks and graph-based representation learning, with a focus of what types of ideas inspired these and how graph-based representation learning is related to some other fields. There were three main domains of historical motivations that led to graph neural networks. The first one was based on convolution and graph signal processing as means to basically generalizing convolutions from Euclidean to non-Euclidean graph domain. The second was the major similarities between the mechanism by which graph neural networks operate with the message passing algorithms and its analogy to the message passing algorithms that were proposed for many of the probabilistic inference applications and graphical models. This actually is the one that I personally find most illuminating when talking about graph neural networks. The third connection that was discussed a lot was the connections between the graph neural networks and motivations and analogies to the Weisweiler-Leman graph isomorphism test. This is pretty interesting and also sheds light on the importance of graph neural networks. And by this, I mean the fact that three kind of different domains of motivation have led to its existence. First, let's talk about graph neural networks and graph convolutions. The book mentions that in terms of research interest and attention, the derivation of graph neural networks based on basically the connection to the graph convolutions is the dominant theoretical paradigm. The question that we need to be asking is, how can the notion of convolutions be generalized to graph-structured data? And this is essentially the motivation of graph neural networks that was rooted in graph signal processing. Let's consider two functions f and h. The convolution of f and h on point x, as defined like this, is going to be defined like that. Let's consider a signal like this. If you consider f to be a function that is constant for a duration of t and has the domain of basically entire R, and if you also consider the h to be the same function, you can see that based on this definition you have a shift, you have a transform, and then you have multiplication and then integration over the following curve, which means that you can consider that this would essentially be like this. So sliding this signal forward and then multiplying and computing the integration leads to this triangular shape result. That was just brought here to just shed more light on how convolution works. Now there is an important relationship between the time and frequency domain when talking about like digital signal processing and things like that. And that also has to do with the definition of Fourier Transform and the relationship between convolutions and that, which basically says that if you are interested in computing the convolution of f and h at point x, you can do it easier by taking the Fourier transform of f and also the Fourier transform of h, multiplying them together, and then taking the reverse or inverse Fourier transform. Now having a fx, Fourier transform of it would be computed like this. You have the f, you multiply it with this value, and then you integrate it over this value. And this gives you that. In the case of discrete data, where you have like a finite domain of t being 0 to n minus 1, you have this circular notion, meaning that this is called a discrete circular convolution, by the way. Domain will be 0 to n minus 1. So you have f, you have h. This time you have t minus tau, but you also have this mod n because of this limitation. Now in terms of Fourier transform, you will have this. Based on what we know about the complex numbers, we know we can expand this into this. Now interpreting this, basically this notion, you can see that Fourier transform has to do with how to represent a signal as a weighted sum of complex sinusoidal waves. This here, that sometimes often is written like this part is going to be the frequency in radian. And when k goes very high, we basically would call them high frequency components. With all this discussion of low and high frequency components and basically the translation of convolution in time domain to multiplication in frequency domain and things like that, we can consider that when we're talking about f and h in this context, we're kind of talking about filtering, as it has to do with different frequency components as well and how they are impacted. Now here's an important property for convolutions. Considering G as the filter here, you can read it like this. Translating a signal and then convolving it with a filter is equivalent to convolving it with the filter and then translating the signal. This is also equivariant to the concept of Laplace operator or difference operator when we're talking about discrete univariate signals. Namely, if you consider delta f t to be ft plus 1 minus ft, you can see that if you're considering delta ft convolved with gt, you basically would have ft plus 1 convolved with gt minus ft convolved with gt, which would essentially be f convolved g at point t plus 1 minus f convolved g at point t, which is delta f convolved g at point t. And based on this definition, again, you can write it as gt plus 1 convolve ft minus gt convolve f, which by factoring f out would be delta g t convolved with f. Now let's say you have a discrete time varying signal, meaning you have ft0, ft1, ft2, all the way until ftn minus 1, meaning you have basically endpoints. Now one way to view the signal is as a chain graph, like this. Therefore you can represent this function as a vector f, such that if you consider this vector f at, its tth element would be ft. You can see the way we formulated this chain graph and basically put the edges has to do with how signal propagates in time. And then because of the discreteness and, the cycle, we also added this edge. Now a question arises that why would we basically model propagating through time like that? And what is the advantage of that? The idea here is that now you can connect notations such as adjacency matrix or Laplacian of this graph with basically the notion of propagating in time. In this context, and the graph above, if you consider the adjacency matrix, you will have the circulant matrix A that is defined like this at each element, which if J is R plus 1 mod n, the value is 1, otherwise it's 0. You can see that now if you multiply this by the vector notation, you're going to get another vector, and now if you look at the tth element of this, you will get f of t plus 1 mod n. And you can easily see that now if you consider the Laplacian of this graph, and you basically multiply that matrix with the vector representation of this graph, you will obtain this value. Which is very connected to the difference. Now you can see that when we're talking about the adjacency matrix here, multiplying that by the basically the vector of representations will be the same as basically propagating them forward, and multiplying by the Laplacian matrix, it's about computing the difference between the value of a signal at a certain node and all of its immediate neighbors. And that would be the use of Laplacian here. Now you have this view of transforming a signal f that then you represented it with a graph by multiplying it with a matrix. Now you can use that same thing in basically redefining the convolution here. So if you have convolution of f and h at time t, you have this. Now you can define it like this. And you can see that's the same thing. Now this basically means that you want to represent convolutions as a matrix transformation of the signal. You have to have certain properties in your QH. One of them is the commutativity with the circulant adjacency matrix, meaning that you need to have ACQH, meaning QH multiplied from the right, be the same as this. And you need to also have that like this. And it can be shown that a QH that kind of satisfies these properties can be defined as a polynomial of the adjacency matrix, meaning that for 0 to n minus 1 you have a coefficient and you have a certain power of the adjacency matrix involved. And you can think about it also as a polynomial functions of the shift operator. Now that we have talked about discrete time-varying signals and the fact that shifts and convolutions can be represented by basically this type of matrix multiplication with the representation, so let's start generalizing these notions a little bit. So far we said that considering a discrete and time-varying signal f defined like this can be essentially be corresponding to a chain graph such as this. And we basically use the adjacency matrix to kind of represent the shift and propagating. Now, in this specific case, when you have a node, you propagate basically from one node to another. And we talked about the circulant adjacency matrix. Now we can actually generalize these notions and kind of define the QH, which was basically the matrix version of the convolution that we discussed, such that with the properties of commuting, with basically when you are considering adjacency matrix and Laplacians, you can essentially use any type of adjacency matrix this time. And the only basically the constraint on QH would be the commutativity when considering adjacency matrix or the Laplacian. Now this time, let's consider an arbitrary adjacency matrix, not a necessarily circulant one. Now you can again define this convolutional filters like this. And in this notation by A0, I mean I. Note that this time the adjacency matrix could involve, for example, representing structures such as this. So overall speaking, we have now a spatial construction of convolutional filters on graphs. Now let's say you have a certain value associated with each one of these. And I mean a value, meaning that a scalar value for each node. If you consider QH and you multiply it by x, you will have this. One thing you can see here is that this power of adjacency matrix basically directly has to do with how many hops of neighborhood you are going to consider when updating the value essentially for a certain node. And these alphas here are controlling the contribution and the strength of the information that comes from the k-level hops. Now you can easily generalize this to the notion of vectors per node. And each one of these could be treated separately as like a channel of information. So essentially the vectorized format of that would be, instead of multiplying QH by A, basically a vector in which each element is associated with a node, this time you are multiplying it by a matrix in which every row of matrix X, so matrix X is a member of RVM, and each row of X is going to be a feature vector associated with a node. And this value would be like this. Now let's discuss graph convolutions and its relationship to the message passing graph neural networks. Note that, first of all, based on what we discussed, one layer of message passing is basically applying this convolution filter, based on the material that we just discussed. Now, of course, you're going to have to combine it with certain learnable weight matrices and nonlinearity. Now, message passing can be sort of looked at as a generalization of the simple linear filter that we have here, as well as basically using certain nonlinearities and learnable weights. Let's discuss an important point about commutativity. So previously we mentioned that QH can be defined like this. And this has certain properties. The first thing is the commutativity with the adjacency matrix. Now, what exactly this means from the perspective of intuition, this basically means translation equivariance. However, we need to note that this does not necessarily mean that if you consider Laplacian of the matrix as well, which is D minus A, or any normalized variant of that, we do not necessarily have the commutativity between the Laplacian and the QH. Even though we saw that for example, for the chain graph that we had the commutativity for both, in the general notion, it doesn't apply. What this means is that in general case, from the practical standpoint, we have a choice between basically choosing how to define QH, so that whether we have commutativity with adjacency matrix or with some version of Laplacian. The book also points out the fact that the theoretical underpinning of this types of trade-offs based on what do you choose as your definition of QH is still an open area of research. The two choices that are often observed in practice is the symmetric normalized Laplacian defined like this, or the symmetric normalized adjacency matrix, which is defined like this. Now the question is, why are these two are essentially used mostly in defining the playing the part in the polynomials defining QH? There are two major reasons for that. One is the fact that they have bounded spectrums because they are also normalized, and this gives this basically leads to good properties in terms of numerical stability and things like that in practice. And the other reason is that they are simultaneously diagonalizable. This can be read as they have the same eigenvectors. Think about the eigen decomposition of these two symmetric normalized matrices. If you consider the symmetric normalized Laplacian, which was defined as this, sorry, this is L, you can consider that as being this. And the reason why is obvious, because you have d minus 1, d minus half, and here you have the unnormalized Laplacian, which was d minus a, unnormalized version of the adjacency matrix. And then you will have, which this part is the symmetric normalized adjacency matrix. So let's look at the eigenvalue decomposition again. So you have LSIM defined like this, and this would be the eigen decompositions. Now you know that this is also going to be A minus symmetric normalized adjacency matrix. Therefore, symmetric normalized adjacency matrix would be I minus U lambda U transposed, which is going to be, because of the orthogonality, basically the orthonormal property of U, you will have this, which is going to be the same as this. So you can see that they share the eigenvectors. What this means basically has to do with the definition of commutativity. And because of this property that they share the eigenvectors, if you define your filters, your QH, based on one of these ASIM or LSIM, it's going to basically imply commutativity with the other one as well. And this is a desirable property because of the reasons we discussed. Now we'll shift our focus to spectral graph convolutions. So the term that is actually important here is this spectral term. Previously we discussed basically convolutions based on a discrete time-varying signal, and we basically got from there to a chain graph and then to a generalized notion of graph, and we defined convolution like that. However, one thing that we ignored, even though we focused on things such as basically translation equivariance and things like that, and commutativity between Laplacian adjacency matrix and the QH, one thing that we kind of ignored was the relationship between convolutions and Fourier transform, and that spectral decomposition notion that comes with it. Now, this chapter, we're going to focus on some sort of extension of Fourier transform to graphs. The objective here is to focus on the spectral perspective of basically graph representation learning and show that this spectral perspective also helps to recover some of the same results that we discussed before, as well as also teaching us a lot more about some more general notions of graph convolutions. First, let's talk about Laplace operator. Let's consider an arbitrary smooth function f with Rd as domain and R as range. You define the delta operator or Laplace operator as this. Which you can read it as divergence of the gradient. And you can see that it has to do with the slope of variations between a point and its neighborings. Let's think about the general discrete graphs. If you have the Laplacian there and you have a vector x with elements associated with a scalar value per node, if you look at the ith element of this, you basically have d minus a. And you have the ith row of this multiplied by x. Now you can also write it like this, which showcases the relationship between this and the definition we just gave. Note that this degree matrix here also has a relationship with how many outgoing edges are from the row ith of the adjacency matrix. So you can kind of bring it like this here, and this part is going to focus on the first part of the Laplacian matrix. And then this part is also obvious, and obviously you're summing over the columns. So in this notion, you're looking at the differences between a certain value and its neighbors. There's a lot to discuss with regards to the definitions of Laplacian and how it is related from the continuous perspective to the discrete perspective and things like that. One thing to note, first of all, is this relationship. Let's talk about continuous Laplacian first. So we define the continuous Laplacian as basically the divergence of gradient. And the way we want to formulate this so that basically we can understand the relationship between this and the discrete is that we are somehow talking about change between a point, values of a point and its neighbors. Now, when we're talking about divergence, we're talking about an operator that will be applied on a vector field and is itself a vector operator, and it results in a scalar field result. Now, considering that our vector field for f is gradient, let's say a three-dimensional f like this. In this case, basically f is a continuous vector going from R3 to R. When you apply divergence to this, you're going to have this. Now, in order to kind of understand how things work, so divergence has to do basically with the outflux of this vector field. And gradient has to do with these partial derivatives here. Now, to understand this better, consider the one-dimensional case. Based on the definition above, we have this as the Laplacian, right? And also, just at the back of your head, just remember the possible connections with the Hessian matrix as well. It's kind of a good way to think about it. But this is the one-dimensional version. Now think about it from this infinitesimal perspective here. Let's say this is point x. When you're defining this, you can sort of approximate it as something like this. Ignore the normalizer value for now, but it'll be proportional to essentially this. Now, if you kind of focus on fx now, you can see you have this. Now, again, focusing on x as a central node, there is this negative sign relationship between the discrete version of the Laplacian and the continuous version. So if you kind of multiply everything by -1, you will have this format. You can see that this is, again, similar to, kind of aggregating the difference between a certain point and its neighbors. So it also has to do with basically how much variations are we going to expect going from a certain point to an infinitesimal neighbor around it. Now, going back to the definition of the Laplacian applied on graph, we said that this is Laplacian vector. Say we multiply it by a vector x, in which x is a member of Rv with a scalar value for each one of the nodes. We said that it's going to be defined this way. So we can see that there is this analogy between them because it also shows basically the difference between a value at a certain node and their neighbors. Now, there is this important property about Laplace operator, and that important property is that the eigenfunctions of this operator correspond to complex exponentials, meaning that, considering, for example, this simple case, this is x, by the way, you're going to get, basically, you're going to have, first of all, you're going to have an I2. So this negative sign will be taken care of. And then you will have 2ps to the power of 2 e 2pist. So here we have basically the complex exponentials making up the frequency components when we were talking about the Fourier transform. One can verify that if you consider that circulant Laplacian that we discussed when we were talking about discrete time-varying signals, that LC, which was a member of Rnn, has these eigenvectors, uj, in which wj is defined like this. Now, we'll talk about the fact that we can generalize the Fourier transform definition to arbitrary graphs based on essentially the connection between the eigenfunctions of the Laplace operator and the components of the Fourier transform. So again, consider a Laplacian matrix like this and the eigen decomposition of it, which is formulated like this. The matrix U can be defined as graph Fourier modes. And we can see that this diagonal matrix of eigenvalues is also very similar to essentially the corresponding frequency values when we were talking about Fourier transforms. And we essentially use the eigenvectors of the Laplacian matrix to define the Fourier modes for it. This means that if you have a function f or a vector f that has a certain scalar value for each node of the graph, you can consider U such that the Laplacian matrix is defined like this, and say that S is going to be this. Now this is going to be the Fourier transform of a signal or a function defined on a graph. And the inverse operation of that, again, having the orthonormal assumption of U, you will have it as US. This is going to be inverse Fourier transform. Now, how do you define graph convolutions here? Again, we have the understanding of basically what Fourier transform and the spectral components mean. So the graph convolution between f and h is going to be defined based on pointwise multiplication of the Fourier transform and then taking the inverse Fourier transform. So this is for the inverse Fourier transform. And this is for Fourier transform of f, pointwise operation, Fourier transform of h. Note that U is the matrix of eigenvectors of Laplacian. So again, consider this. One thing you can note here is that now you can have this theta h here. Theta h basically is graph Fourier coefficients for filter h. If you think about it, you have this, which is like that. And bringing it here, you can rewrite this formula as U, the diagonal matrix obtained from vector theta h, U transposed, and then do this. Now essentially this can be directly observed as essentially a non-parametric way, but the problem with that case would be that the structure of the graph would not be considered if you consider the theta h in its general sense. So in order to have a meaningful convolution definition, theta h can be essentially parameterized based on the eigenvalue of Laplacian. This means that you can write theta h be a polynomial of Laplacian. If you do this, you can see that f convolved with filter h would be U, the polynomial of lambda, U transpose, and f. So this essentially can be seen as a polynomial of Laplacian multiplied by f. Therefore, you have the commutativity, for example, with Laplacian. And given that now you're working with the polynomials of Laplacian and you have added this constraint on the theta edge, now you have this boundness in terms of locality as well, meaning that in the polynomial, when you have Lk, you are working with the k-hop neighborhood of a certain node. Let's discuss something interesting here. And that interesting thing is talking about essentially frequencies and the relationship with eigenvectors of the Laplacian. There's no clear intuitive definition of high frequency and low frequency components, the same way as we have, for example, for continuous signals. But here we can, again, still make some analogies. Let's consider this first. We knew that if you consider Laplacian and you do this, you would have essentially for every edge in which this value was non-zero, you had this. Consider that these are eigenvectors. This ui is for example, an eigenvector of Laplacian, which we related to the frequency component in the Fourier Transform. Now you also have the Rayleigh-Ritz theorem, which stated that if you want to solve this, there are the eigenvectors of the Laplacian that actually do this minimization. What does this mean? It means that the smallest eigenvector of the Laplacian is going to correspond to a signal. So I'm basically reading this exactly from the book because this part is actually important. Together, these facts imply that the smallest eigenvector of the Laplacian corresponds to a signal that varies from node to node by the least amount on the graph. So varies from node to node by the least amount on the graph. Then you have the second smallest eigenvector corresponding to the signal that varies the second least amount, and so on. And you can see that this is the analogy between like high frequency, low frequency in the Fourier transform over the continuous signals. Now, to gain a better historical perspective, let's read this part of the book together, which is about the fact that many of the earliest works on graph neural networks can be directly mapped to the definition of graph convolution. These two equations that are at the core of these methodologies are basically associated with definition of graph convolution that we gave, which was based on a polynomial of the Laplacian of the graph multiplied by f. In this work, which is one of the early works, the authors experimented with a non-parametric spectral filter, as well as a parametric one. And they defined this polynomial via a cubic spline approach. Then there was this work that used Chebyshev polynomials, which have, first of all, an efficient recursive formulation, and second, various properties that makes them suitable for polynomial approximation. And there were some other techniques as well. Now let's talk about graph convolutional networks. The key insight for them from the book is that we can build powerful models by stacking very simple graph convolutional layers. In this work, a basic graph convolutional neural network layer is defined as HK, and nonlinearity here is a normalized version of the adjacency matrix, the representations from the previous layer, and learnable weights. So this nonlinearity and learnable weights are what we are adding to the notation of the convolutions. And A tilde is defined as D plus I, like this, times. So you can see here that you're considering the self loops. So again, looking at this, you have simple graph convolution, you have learnable weights W, and you have the nonlinearity sigma. In general, we can see that this definition is pretty similar to this generalized version that we defined in chapter 5. So you have a network's basically neighbor influence, and you have these self-representations for the node. Now first, let's talk about the fact, so previously we mentioned that considering the Laplacian of a graph and considering the eigenvectors of that, we know that like the smallest eigenvalue from the smallest to going to the larger eigenvalues, we are kind of going from low frequency to high frequency, and that notion of frequency defined for the space of graphs had to do with how much difference would we expect to see in going from one node to its neighbors. Now this smallest eigenvalue for the Laplacian, given the fact that Laplacian is something minus a multiplied by something and something like that, there's going to be this negative relationship. So the smallest eigenvalue for L is somehow corresponding to the largest one in the adjacency matrix. And to shed more light on this, let's consider L sim and A sim as before, which was the symmetric normalized adjacency matrix and symmetric normalized Laplacian matrix. Now in a simplified notion of graph neural networks, we can have this update rule defined like this. So you are removing the nonlinearity just for the sake of analysis. This basically means that at every point you're kind of considering certain average values over neighbors. This means that if you consider the original features of these nodes, after k iterations you have something like this. So this W is going to be just some linear weight, and then you have this part. Now we know that the dominant eigenvalue for this normalized version of the adjacency matrix is going to be 1, which means that there exists this fixed point in which you will have something like this. Meaning that if you take the representations and if you do this averaging, you're going to obtain the same values. This basically means the higher the k is and the higher powers of adjacency matrix kind of are emphasizing the lower frequency components in that spectral notation that we discussed. Therefore, it's kind of equivalent of applying a low pass filter on this notion of frequency that we defined on graphs. There have also been several recent works focusing on basically removing this message passing component from the graph neural networks and simplifying that equation by having this new equation. Now in this case, f of a is a deterministic function that is going to be applied on the adjacency matrix, and it's going to give you fa. In this notation you have x also, which is of these dimensions. So you have m-dimensional feature vectors for each one of the nodes, and you have these two multilayer perceptrons as well as dense fully connected neural networks. And in some of the recent works, for example, this reference of the book, f of a is defined as this, meaning you have this formulation of a, this variant of adjacency matrix, and then you define fa as this. The intuition behind these types of approaches is that, based on the book, so we often do not have to interleave trainable neural networks with graph convolutional layers. And basically they have shown that this kind of simplified approach actually outperforms more heavily parameterized message passing based models such as GraphSage and many of the classification benchmarks. The idea is that instead of doing that heavy message passing, we use neural networks. First, we use them to learn feature transformations in the beginning, and then we also apply a deterministic convolutional layer to leverage the graph structure, and then we apply another multilayer perceptron at the end. The book also mentions several works, for example, that showed that convolutions defined based on this notion that we define achieve the best performance on empirical tasks, and that there are some theoretical justifications for this as well, which has to do with the fact that adding self-loops is going to shrink the spectrum of the corresponding graph Laplacian, and it kind of reduces the magnitude of the dominant eigenvalue, and intuitively self-loops decreases the influence of faraway nodes, and kind of put a more focus on the local neighborhood of the nodes. Next, we want to talk about probabilistic graphical models and their relationships with graph neural networks, which formulates another alternative theoretical motivations for these models. In this notation, the final embedding that we have for every node in the graph, assuming that again you have this graph, is called a latent variable that we are trying to infer. The assumption is that we have observed the graph structure, meaning that we have access to the adjacency matrix that encodes the graph structure, and we also have input features. And we want to use these to infer the underlying latent variables. Now, message passing algorithms have some uses in probabilistic graphical models and algorithms for variational inference, and we want to show that there is a connection between that and what we defined as graph neural networks. Note that this connection was first noted in this work. The first thing we want to talk about is Hilbert space embedding of distributions. Consider a random variable x, which is m-dimensional, and consider the probability distribution p defined on this x. Then also consider the feature map phi, which could be potentially infinite dimensional, that can satisfy this formulation, meaning mu x is going to be probability of x, so at any point x, and then the feature map for x over the entire space. Now the key idea for Hilbert space embedding of these distributions is to select this feature map in a way that this transformation becomes injective, meaning that mu x, which is a representation and could have like a dimension d, is a sufficient statistics for obtaining the probability distribution over random variable x. So you are representing a probability distribution over an m-dimensional random variable as mu x. This becomes very important in defining this relationship between GNNs and probabilistic graphical model message passing methods. Now let's talk about graphs. So in defining these graphs, and basically especially when we are interested in the relationship between these graphs and like the graphs that are used in probabilistic graphical models, is that having an edge between two nodes most often indicates a certain relationship between them. Therefore, you have some understanding about the dependencies between different nodes. So when you have a graph G, set of nodes V and set of edges E, you define a Markov random field. So this assumption means that if you consider the probability distribution over the space of all of the node representations and latent representations, this is going to be proportional to the non-negative potential phi, and this is again multiplication, and you have psi for every edge. This means that this distribution over the initial embeddings, node embeddings, and the latent variables can be factorized according to the graph structure, meaning that you have this potential here that indicates the likelihood of a node feature vector xv given its latent variable zv. So again, it's proportional to the likelihood of observing xv, the node emitting xv, given its latent representation zv. And the non-negative potential psi kind of controls the dependency between node u and v that are connected by an edge. Again, this is an assumption here that node features, meaning x's, are basically determined by their latent embeddings. And we also assume that these latent embeddings for the connected nodes are not independent from each other, meaning they depend on each other. Most often, in the context of probabilistic graphical models, phi and psi are going to be defined based on some sort of either exponential family of functions or something like that. But in this case, we are kind of interested in implicitly learning them. And here, Hilbert space embedding of distributions is going to be useful. So our goal is to infer the distribution, again the probability distribution, over latent embedding for nodes V for all of the nodes of the graph. So for all nodes of the graph. So again, our goal is to infer this. And we also want to implicitly learn the non-negative potential functions phi and psi. Now a key step is to compute the posterior ZV given XV, which means you have a particular set of latent variables and basically you have the observed features and you want to find this probability. As the book mentions, even if phi and psi are properly defined, computing this is not always tractable. One approximate method is basically employing the mean field variational inference, which means you can factorize this as the multiplication of probability distribution over these latent variables QV. Sorry, the latent variables are ZVs and Qs are the distributions. So QV here is a valid density function. And again, here the mean field variational inference assumption is that this posterior distribution here can be factorized into V independent distributions, so one per node. Now, in order to find Q, we need to focus on Kalbach-Lever divergence as a distribution to distribution distance to minimize, meaning that you're going to have to consider this that we defined above with the true posterior, which is this. So the major problem with this big formula here is that we again have to have knowledge of the true posterior. However, it can be shown that, from different techniques, and it's kind of outside the scope of this lecture, that you can show that the QV ZV that minimizes this KL must satisfy this fixed point equation. So see here, CV is going to be a constant value and it doesn't depend on QV on ZV or on ZV in any sense. In practice, we're going to have basically a random guess and use this fixed point equation as a recursive function and try to iteratively compute this. The important things here, first of all, was employing that mean field assumption and that factorization assumption. And the other thing is that in this recursive formula, we can see that approximating QV on ZV, it has to do with the node feature representations X, these marginal distributions over the QUs, and this becomes pretty important. So basically you're having a function of a set of neighborhood marginals, so you have neighbor marginals here, as well as a function of node features. And this becomes pretty similar to the message passing that we have in graph neural networks, except that we are working with distributions here. Now, one thing that Hilbert space embedding can help us with is basically representing these distributions as embeddings, meaning that we can say mu v is going to be the RD integration of QV ZV and this is going to be a d-dimensional representation for this distribution QV. With this, you can define mu et is going to be a constant plus a function of the previous and then node features. And these Hilbert space embedding representations of the neighbor marginal probability distribution. So we have this aggregation and updating the same way that we discussed the message passing over graphs. Now it is worthy to note that given some supervised task, we can actually learn these embeddings mu v's via supervision signals. This way we can basically get and obtain mu v's, and these learned embeddings could correspond to some probabilistic model, which is a lot more straightforward than defining a concrete probabilistic model and then getting to this. It is important to note that there are further ways to connect PGMs and GNNs. There are different variants of message passing algorithms, different approximate inference algorithms and things like that. They are all also discussed in this major work. And there have also been works that were exploring how GNNs can be integrated more generally into probabilistic graphical models. And this area, again, is a rich area with vast potential for new developments. Next, we will talk about graph neural networks and the relationship between them and graph isomorphism tests. Now we want to talk about the final theoretical motivation behind graph neural networks, which is basically their connections to different tests for detecting graph isomorphism. So here's the objective. Having a basically isomorphism detection algorithm or isomorphism test algorithm, in this case the Weisweiler-Lehmann algorithm, we want to see how GNNs can be introduced as a neural network variant of these algorithms. Now, in addition to talking about the motivations of GNNs rooted in graph isomorphism, this also provides us with tools to analyze the power associated with the graph neural networks in a formal way. So let's just start going through the book. The isomorphism test is defined based on two graphs. Let's say you have G1 and G2. If these two are isomorphic, this means that they are identical. In other words, it means the structure that the graph represents is exactly the same. The only thing that could be different is the ordering of how you associate a certain node name with them. In terms of the notation, let's say you have the adjacency matrix A1 for graph 1 and adjacency matrix A2 corresponding to graph 2. If you have these two graphs be isomorphic, you can write that G1 and G2 are isomorphic. So also consider, say, X1 and X2 being the matrix of basically feature vectors associated with them. So these are, for example, of R. So n-dimensional features. So G1 and G2 are isomorphic if and only if there exists a permutation matrix P such that you can permute the nodes in one to essentially reach to the others. And that also results in permuting the node representations. Again, we will have the same correspondence. So this was a simple definition. One question is, can we just define P like this to solve the optimization problem? That is essentially this. Now this requires basically going over all possible options that you have for permutation, which in this case is going to be of this order of complexity. This is the number of this is basically cardinality of the set of nodes, or basically number of nodes. And this is a very large number in practice, therefore this thing becomes untractable. Now the thing to note here is that graph isomorphism is an NP indeterminate problem, meaning that it is known that it is not an NP complete problem, but there is no general polynomial time algorithm that can solve it. However, there are many approximate algorithms, like the WL algorithm that we've discussed before, that can kind of approximately try to solve this. Now, the theory of graph isomorphism can be used in order to quantify the representational power of different learning approaches. Meaning that if you have a graph and if you have a GNN that you can pass it to and obtain a representation for this graph, which is of RD, you can quantify how much information has it learned by asking how useful these representations are going to be if you want to do some sort of a graph isomorphism test. Now, in a perfect setting, the representation for two graphs is going to be the same if and only if G1 is isomorphic to G2, which of course doesn't exist because, again, P is not NP. And if it exists, we probably have to have this. Now let's go to the WL algorithm, or Weisweiler-Lemon. We start with the simplest approach of it, which is 1 WL, which has to do with individual nodes. We will talk about KWL later, but for now, let's focus on 1 WL. Step 1 is that you assign label L G1 0, meaning the label for node V in graph G1 and in the first iteration. You also have a L for G2 of node V and 0. Again, these are all the nodes in these two graphs. A good choice for this is often the node degree, meaning that L0 for V would be dV for every V in the nodes of the graph. Now the other operation is going to be this. In order to get to the ith iteration label for the graph, you're going to have hash, and you basically have the previous label of the node and also the multiset of the labels of the neighboring nodes. Note that repetition is allowed in a multiset. Step 3 is basically repeating the step 2 until, so repeat 2 until when you have this equal this for all the nodes in Vj. By the way, let's make these J2. The next step is constructing this multiset for Gj, which is again the label for each one of the nodes and across all of the iterations. And then you say that G1 is isomorphic to G2 if and only if these two multisets are equal. And this algorithm is known to converge in at most V iterations. However, even though this test is mostly successful, there are cases in which it fails. And one example of this is this cycle. So this is G1 and this is G2. This is one of the cases that if you run the WL algorithm or one WL algorithm is going to fail. Now the relationship between GNN and WL algorithm is that GNNs are known as very analogous to them and as a continuous and differentiable analog of these WL isomorphism tests. Now this theorem is going to formally define the relationship between graph neural network and the Weisweiler-Lehmann algorithm. Define a message passing graph neural network as follows. So you have to define a message passing graph neural network like this. Any graph neural network that has k message passing layers of this form. Again, you have the update operation and you have the aggregate operation. Now we're not done. The aggregate function has to be differentiable and also permutation invariant. Also, the update function has to be differentiable. Also suppose that we only have discrete feature inputs as the initial layer, meaning that HU iteration 0 is going to be XU, which is a member of ZD. And this applies for all the nodes. Now with all of these assumptions, HU of iteration k is not equal to H3 of iteration k only if U and V have different labels after k iterations of this algorithm. And by this I mean the WL isomorphism test. Now the important implication of this theorem here is that graph neural networks are not more powerful than the WL algorithm when you use discrete information as node features. Another result from that is that based on this definition of MPGNN, you can say that there exists an MPGNN in which after k iteration for node U and node V, we have this if and only if and only if they have the same label after k iteration of WL. This means that there exist powerful MPGNNs that are as powerful as WL test. So another question when assessing the power of graph neural networks based on the WL algorithm is which one of the graph neural networks that we have discussed, which one of the message passing versions are at most power, meaning that they have the same power as a WL algorithm. It can be shown that this formula actually works. So I have the W self, the W of A, and this B. So this was the simplest version that, one of the simplest versions that was discussed in chapter 5 of the book, and this actually has the power similar to the WL algorithm. We need to note that one of the other properties that actually is kind of required in order to reach the representation power of a WL algorithm is the fact that the aggregate function has to be injective, which is not applicable to many of the methodologies that we have discussed. In this resource, the authors have defined a minimal GNN model. This model tends to have a few number of parameters, but is still going to be as powerful as the WL algorithm. This model is called Graph Isomorphism Network, and this is the update rule for this model. So in order to obtain the kth iteration, you have this MLP applied on this. Now this epsilon is a trainable parameter. You have the previous representations. And also you have this. Please refer to this source for more information on this. As the book mentions, discussing what kinds of graph neural networks can be built, that they be more powerful than the WL algorithm, is an active area of research. First of all, let's talk about relational pooling. One thing we discussed was this 6-node cycle and 2 3-node triangles. Now this would be G2 and this would be G1. We mentioned WL algorithm and the MPGNNs that were limited in power to the WL algorithm cannot basically do the isomorphism test on these two graphs properly. The main intuitive idea behind why this happens is because of the limitation in the aggregate and update operation, meaning that when you're considering each node in this system, each node can basically kind of detect two neighbors, but there is no information regarding whether or not these two neighbors are actually connected to each other. One huge limitation for message passing approaches is that they generally fail to identify close triangles, and that is a considerable drawback. Now, there have been this work that tried to address this by adding a unique node ID feature. To see how this works, consider an arbitrary message passing graph neural network with adjacency matrix A and node features X. In this work, you basically are going to concatenate these ID features as well. Now, with this I being an identity matrix and then this being a column-wise concatenation, meaning that you are basically adding these features to the node features. So you're adding you're concatenating the node features with a one-hot vector representing the node identity. Now you can essentially distinguish between the two graphs. However, you have lost the very important property of permutation equivariance. We know that for a normal MPGNN, we had, if you consider this MPGNN, and if you would permute the nodes, this would essentially be the same as applying the MPGNN on A and X and permuting the outputs. Now, the way they deal with this, and the term basically relation pooling, they involve basically marginalizing over all of the possible node permutations, meaning that you have your MPGNN, you have an arbitrary permutation, and you use these ID features. Now what you do is that you consider all of the possible permutations, and this becomes the relation pooling graph neural network applied on A and X. So you have extra representational power. However, the complexity of the algorithm is going to be terribly higher. And naively speaking, it'll be again of this order. In the proposed work, basically meaning this, they mentioned that, again, good properties can be achieved by trying to approximate this formula, meaning, for example, focusing on a subset of possible permutations and things as such. So the main two problems with this algorithm is that, first of all, it's going to be very computationally complex, and second of all, we know that it is more powerful than WL, but we don't know how much. The WL algorithm that we discussed so far focused on individual nodes. A generalized version of this algorithm is KWL. The idea here is that instead of focusing on individual nodes, we are going to focus on size k subgraphs. The steps of this algorithm are as follows. First, let U1 to UK be a size k subgraph of this graph, in which you know none of these two nodes is the same. Now you define the initial label of this subgraph as this, and this initial label for two subgraphs are the same if and only if they are isomorphic. Now here's the iteration. So here's what you have. You have the label representation for the subgraph in the previous iteration involved, and you also have this multiset, which means that you have the label of the subgraph neighborhoods, j for 1 up until k. And neighborhood j of subgraph S is going to be defined like this. You have the multiset of so you have that, set of nodes that you had. You remove the uj, you substitute it with v, and this v would basically cover all of the possible nodes. As expected, step 3 is repeating step 2 until convergence. And step 4 is building the final multiset. For all of the size k subgraphs. And this is basically going to be summary of all of these subgraph labels. Now there are some properties about the generalized version of the WL test. One property is that for k larger than or equal to 2, you know that k plus 1 WL is a strictly more powerful test than KAWL. Noting, however, that if you have k larger than 3, basically the solution will become generally computationally intractable. And the reason is that you're going to have to again deal with the graph isomorphism for graphs of size k here. Now, can we combine basically GNNs and use some analogy to this generalized version of WL algorithm? The answer is in this article, in which they develop a KGNN approach, which is differentiable and continuous analog of KWL algorithm. Focusing on learning representations, this time for subgraphs, and doing this message passing according to subgraph neighborhoods. And again, you have the problem of basically the combinatorial increase with k in the message passing time complexity. This work also proposed that we could focus on invariance and equivariance in designing GNNs to again reach the same power as the KWL test. We saw that in message passing graph neural networks, if you use a permutation matrix P, it would basically be the same as getting the output of A and X and then permuting it. Now this is focused on equivariance, but we can also define this pool function which basically takes a representation for each one of the nodes and obtains essentially a graph representation that represents the entire graph. Now having this, it's easy to see that if you apply the message passing GNN, adjacency matrix A and features X, and then do this pool operation on it, it'll be the same as basically doing the pooling operation on the outputs of message passing GNN on the permuted version of information. Which is kind of intuitive because you already know that if you, for example, permute the features, you're not going to impact the any sort of a pooling operation that kind of applies to the entire graph. Now let's go back to this work. Let's say you have a matrix S or tensor X of this dimension. And let's say you basically represent it as a order k plus 1 tensor, meaning that you have the first k channels allowing you to index by the nodes, and the last one being a representation. Now you can define this notation that if you have a tensor X like this means basically permuting these channels. Now if you want to define a linear layer or a linear operator, you can do it, and then you can define equivariance and invariance based on that accordingly. Basically, let's assume that you have this linear operator, and the idea is that you want to take the representation from dimension d1 to dimension d2. Now consider this being a generalized tensor product. This is how you can define equivariance, and this is how you can define invariance. So again, you have to work with permutations, and these definitions should hold, these constraints should hold for any permutation sampled. Now for equivariance, if you apply this linear operator on your data, and then if you permute it, this is the same as basically applying this operator on the permuted version of this data. Now this is equivariance. In terms of invariance, you will have this. Now if you consider an equivariant operator L that takes this to this, it will be equivalent to a tensor version of L, which is of this dimensions. In this case, I think the notation used in the actual article from ICLR 2019 is better. Let's just start with, for example, the adjacency matrix that is of dimension n by n being the cardinality of set of nodes. In the actual article, this notation is used. If X is a matrix like this, vec of X is this way of reshaping it. And this one, you can basically consider it a D, but it doesn't really matter at this point. And then bracket applied on Vx is basically reshaping it back to this. Now, if you consider a general linear operator n by n, R, L could be represented as 1 by n2. Now, when is this invariant? It is invariant if and only if this holds. Now, this means that if you consider the Kronecker product and its properties, note that in this case you have basically this. Now in the case of equivariance, you have this operator. And this time your L is a member of n2 times n2. Which if you think about it, it'll be this. Now you can read the rest of the article for the details on the method, but that was basically just some talk about the dimensions. Now going back to the book, they show that with the notation of the book, If this equation holds for any permutation matrix, then this can be used to basically combine the properties related to invariance and equivariance. Note that the dimensions for P could be different depending on equivariance and invariance. And then they showed that operators that satisfy this format can be built such as this, and it has connections to the Bell numbers and things like that. And then they propose a graph neural network model based on these findings and show that it is equally as powerful as KWL. However, the problem with the combinatorial increase in complexity by increasing the number of k still exists, and this method also is computationally intractable for k larger than 3.